disease or some under. This is a medium size. This is a medium-sized session on how to quickly make sense of a research paper. Research papers are reports from laboratories, scientists, engineers, claiming to present a discovery or an invention that might be related to a cure for disease or some underlying development in a tool that's exciting. And if you want to be a bionaut and be capable of navigating the frontier and future of bioengineering, underneath it all, you've got to get to reality, which is oftentimes represented in these research papers, as opposed to newspaper stories. So let's dig in and see how it goes. This is meant to be a lightweight tool you can put in your bioengineering toolkit and keep getting better at over time. I am still getting better at using these approaches and reading research papers. You may be already awesome at this, like a chess master level superstar of reading research papers, or maybe you've never even seen a research paper. You don't know what I'm talking about yet. Don't worry. No matter how great you are, you can become even better or even more greater at reading research papers. We're going to do the short version here, and it's got 4 steps. Make sense of the title, find a claim in the abstract, skim the figures, think of this like a picture book, not a wall of text, and then decide what you think. So let's get into it. For example, let's say I see a headline, bacterial photography. Apparently you can take photographs with bacteria. I thought you could only take photographs with cell phones or film. Let's see if we can find a research paper involved in this space and then use that as an example, should be exciting, to see what's going on in the space of bacterial photography. As an aside, with all these slides, down at the bottom, I'm usually including a link to a website if you want to learn more about what's shown right here. So just in general. Okay, here is a research paper that is representing something to do with bacterial photography. And gosh, it looks intimidating. There's many, many pages, and it's just a wall of text. Let's figure out how to quickly read a research paper. This should be a fun example. So we'll zoom in a little bit. And the first thing we're going to do is we're going to look at the title of the paper. The title is the big bold text at the top. A synthetic genetic edge detection program. That's the first thing I'm going to do. I'm going to read the title. And I'm going to see if I can understand it. A synthetic genetic edge detection program. A program. A synthetic program. A genetic program. A genetic program, like something in DNA. It's a program, like a computer program, but it's a genetic program. And it's a synthetic one. It's not a natural one. It's something that Jeffrey, Howard, Zachary, Aaron, Anselm, Edward, Chris, and Andrew, they must have bioengineered. So, okay, a synthetic program, a synthetic genetic program. I'm okay with all those words. Edge detection, like obviously I know an edge, like the edge of a cliff, and detection, like detected. But edge detection, I'm not totally up to date on. So maybe I'm going to flag those words and say, before I go any further, let me just make sure I understand what edge detection is. Now, how would I quickly try and upgrade my knowledge of edge detection? You know how to do this, not that complicated. I'm going to go to Google or some search, and I'm going to type in the words edge detection. And oftentimes I go right to the images. And so, for example, I see a photograph of a person, and then to the right, it looks like you can sort of see the outline of the face and the hair and the dress. Or if I go to the top middle, I see, what are those, nickels? And other maybe dimes. And then just to the right, this black and white image, the edges are revealed where the coins stop, and then the various etchings or imprints on the coin, the edges of those. To the right, the hat. To the bottom left, a person, a photograph, and then, okay, I can see the outline of the person, their shirt, their tie. It looks like whenever there's a change from one boundary to the next, that's an edge, and so edge detection is finding that transition. Anyway, like I'm spending more time explaining what I'm observing than I actually, do in reality when I'm trying to learn. Another thing which is fabulous, of course, oftentimes is Wikipedia. And sure enough, there's an entry on edge detection, and we can skim this really quickly. Edge detection is using math to identify edges or discontinuities. And I'm just going to skip down. And the purpose here is to detect sharp changes in image brightnesses. This is a little bit too digital world. We're in bio world, but I get the idea. You know, like if there's an image or a pattern, and suddenly a certain property of the image or pattern is changing discretely, that defines an edge, and so edge detection detects such changes or transitions or discontinuities. Okay, great. So now we've got a synthetic DNA program that can detect edges in something. Where's the pattern? Well, it's bacterial photography, so maybe it's in the picture taken by the bacteria, but we'll have to see. Okay, that was step one. How about step two? Can you find a strong claim in the abstract? So the abstract in a research paper is the chunk of text before the paper itself that's supposed to be the summary, executive synopsis of what's going on in the paper. And this is going to be one of the only parts of the paper that I actually read and would recommend you read. Mostly you don't read papers, actually. But the abstract we're going to read, and we're going to read it with a purpose, a ruthless purpose. We're going to try and find a strong claim in the abstract where the authors are making a claim. I say this, right? And right there is a hint. Oftentimes in abstracts, the best claims use first-person declarative statements, like I did this, we did that. So let's read this abstract together and see what we can find as a claim. Edge detection is a signal processing algorithm common in artificial intelligence and image recognition. Okay, that's just background. We have constructed, there we go. They're claiming to have done something. We have constructed a genetically encoded edge detection algorithm that programs an isogenic community of E. coli to sense an image of light, communicate to identify the light-dark edges, and visually present the result of the computation. That's a mouthful, but it sounds like a claim. It's like, we have constructed blah, 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 blah. Next sentence. The algorithm is implemented using multiple genetic circuits. An engineered light sensor enables cells to distinguish between light and dark regions. In the dark, cells produce a diffusible chemical signal that diffuses into light regions. Genetic logic gates are used so that only cells that sense light and the diffusible signal produce a positive output. A mathematical model constructed from first principles and parameterized with experimental measurements of the component circuits predicts the performance of the complete program. Quantitatively accurate models will facilitate the engineering of more complex biological behaviors and inform bottom-up studies of natural genetic rate. Oh my God. Everything after the sentence beginning with the word we is nice. There's a lot there. But the main claim is we have constructed in that sentence. We have constructed a genetic program that gets E. coli to sense a light image and identify the edges in the so produced image. So I'm just going to highlight that. This, I think, is the main claim for this paper. And just like with the title, is there any word in here I don't understand or I want to brush up on before I go further? We have constructed a genetically encoded edge detection algorithm. No, these are all good. Isogenic, maybe I want to understand what that means exactly, because that's a isogenic community of E. coli to sense. Yeah, I think I'm okay with all the other words, but I just want to brush up on isogenic. So let me flag that. And we'll do the same thing as before. Isogenic, dictionary. It's an adjective, having the same or closely similar genotypes. Organisms having the same or closely similar genotypes. What does that mean? The same? Okay, the same. So, like, I don't have the same, I'm not the same as my brother, we're not twins, but closely similar, like are we isogenic? And then what's a genotype? Better double check that. A genotype is a noun, and it's the genetic constitution of an individual organism. So I think that's the DNA of an organism. It's genome. That's the genotype. And then an isogenic population of organisms would all have the same DNA. Or all have the same. I'm going to get rid of this closely similar because I don't know what to make of it. But isogenic is a population of organisms all having the same DNA. So, all right. We're now at a point where we have to make a decision. This is the most important part of reading a paper. We've done our best to understand the title. We've done our best to parse the abstract and see if we can find a claim. And now we have to make a decision. If we can't understand the title, we should decide to not spend any more time with the paper. Or do not read this paper if you cannot understand the title. You'll be wasting your time. Go find another paper. There's plenty of papers. In this case, great title. We figured it out. Okay to proceed. Next, do not read the paper if you cannot find a clearly stated claim in the abstract. Find another paper. The paper will waste your time if there's no claim. There's plenty of other papers. So the most important thing about practicing how to read a paper is to make sure you're not wasting your time on papers that are not easy to read. Unless you, well, just like don't waste your time. There's so many papers. Most of them are okay. All right. And now the example again, we're working with here, very nice paper so far, right? We've got a title we can understand and a very strong claim in the abstract. Even when those conditions are true, even when we understand the title, even when you found a strong claim, don't read the paper. However, keep going. The reason I say don't read the paper is as soon as you sit down to read the paper, it's like sitting down on the couch with a good book and I'll see you tomorrow, right? We're not trying to like savor the paper yet. You know, like if that's your hobby, go do that. But we're just like trying to parse this paper quickly. Right, so it's actually really interesting. How to read a paper? Don't ever read a paper. You're going to parse the paper. All right, so let's see what that looks like when we keep going. And here's where it gets really fun. It's like, think of it like a kid's book, a picture book, because that's what we're going to do next. Instead of reading the paper, we're going to look at the images in the paper, because research papers often come with what are known as figures. And it's like the picture book part of the research paper. And we're just going to take a quick skim, flip through, and look for all the figures. And we're looking for evidence of the primary claim. Now, remember, in this paper, the primary claim is they had made a genetic edge detector. So we're looking for something that is evidence of an edge detector. Here's the first picture I could find in this paper. There's a lot on this figure. There's no evidence here. This is just all schematics. Next figure. I don't know. I don't know. I'm not going to spend more time on this figure. Next figure, figure 3. Mask, in vivo, in silico. I see something called an edge detector down on the bottom left, and I see an image of data that looks like evidence. And then when I go and look at the figure title, figure 3, title, construction of the edge detector from individual genetic circuits. It looks like they're making an edge detector here, and they're showing us that they made an edge detector. And so edge detectors down in D. So if we go over to the figure legend, we go all the way down to the bottom right, we can see the text describing just to the left what's in figure 3D. It reads, a population of cells programmed with a complete edge detector system produces black pigment only at the boundary between light and dark regions. The model solutions are reported in Miller units on the right. Okay, so let me back up. This is a really interesting figure. This has evidence, so I'm going to spend a little bit more time on it. Let me go back to the figure legend at the very top. Underneath the title, it reads, various circuits are constructed. I guess these are DNA circuits, DNA code, and the effect on image processing is assayed or measured, left, and compared to mathematical models, right, predictions. The details and so on, okay. So this middle column that's in black and white, well, let's do actually the top row, the mask. I guess they're having some sort of mask that lets light through the white zone and blocks light in the black zone. And they're putting that mask above a plate, a petri dish, full of bacteria. See that little scale bar, 1.4 centimeters down in the bottom? So it looks like there's a petri dish, a circular plate of bacteria that's about 10 centimeters across. And when they shine light through a mask, the light only hits in the opening, and that's the white zone. And the bacteria that are in the dark make a black pigment. And what's actually happening on the bacterial plate is shown in this in vivo column in the middle. And then what they expect should be happening is shown in the right column, colored in red and blue and green and yellow. And we can see that if they just take a bacterial picture in the top, the photograph, they have a mask that's a star, and the bacteria make a capture pattern of the star. And then if you go down to the inverter, row C, they can flip the pattern. So what was black and white is now the opposite. And then if you look in the edge detector and you look closely, you can see that the darkness is strongest at the border of the star. Okay, so I spent a lot of time on this figure in part because the figure is claiming to provide the evidence in support of the main claim, constructing the edge detector. Let's go to the any more figures? One more figure, as it turns out. This also looks really interesting because the title says edge detection of complex patterns. And so here we see in the top a mask, circle and a circle. When you shine light with that pattern on a plate, you see a circle is captured in the bacterial film, and it looks like the perimeter of the circle is the darkest region. And it looks to me like they have an intensity plot just below the circle, which is measuring how dark it is going across, say, the equator of this plate, and the maximum intensity is at the borders of the circle. This looks like edge detection. Middle, the next one down, I see the mask pattern is a square on the plate, and we see that the perimeter of the square has the darkest intensity. That looks like edge detection to me. What's this thing on the bottom? That looks like, what is it, a silhouette of Alfred Hitchcock. If I have a mask that's shining light onto a plate of bacteria, and the bacteria are responding to the light and then doing edge detection on the light-dark border, we see in the middle, look at that. You actually are capturing the silhouette and the edge detection computation of the Alfred Mr. Hitchcock. Now look, we haven't read any of the paper except for the abstract at this point and some of the figure legends. But what do we have? We have access to the primary evidence, the experimental evidence in support of the main claim that the authors are stating up front in their abstract. And so now we can get to step 4. What do we think? Does the evidence support the main claim? Based on what I can see so far, absolutely. This is a fabulous paper. There's a clear claim in the abstract, and at least 2 of the 3 figures straight up show us evidence that's supporting this claim, that you could make a genetic edge detector and use that to do simple signal processing within a bacterial photograph, a coliroid, not a Polaroid, but an E. coliroid. Do I want to learn more is the next thing then. If the evidence doesn't support the main claim, what am I going to do? It's like, okay, this is a bad paper, but this is a great paper. Wow, what a neat paper. Do you want to learn more? Sure. If I want to learn more, then what I could do is, well, what do I want to learn more about? Do I want to learn more context? Then I might go back and read the introduction of the paper and really savor it. Maybe I just want to learn, how did they do this? I want to read the recipes. I want to go see the methods. What are the impacts of this? If that's what I care about, I might go read the discussion at the end of the paper where the authors might explain how they're thinking and why they think this matters. Related but different is, what questions or ideas do I have or do you have? Are there weaknesses in this work? What are the limitations of bacterial edge detection? What would be the next things to do? Is there future work? Is this good for anything? My dad would ask, like, what's this good for? And other things. But it starts with deciding what you think. Is there evidence in support of the main claim? If no, then the paper's got a problem. Go find another paper. But if yes, then what do you want to do next, right? And have a lot of fun with that. Reflective questions. How many bioengineering relevant research papers do you think are published every year? 100? 1,000? A million? Here's a hint. Go check out this website, PubMed. Just do a Google search for PubMed. And I bet you will quickly find that there's, I don't know, at least 10 million, maybe 100 million. Not every year, but total. And so, like at least a million papers a year. How long does it take to read a research paper? Even with this abridged, like super turbo method, how long does it take? How long have we been going, right? How many papers do you think you could read or parse each year? Could you ever keep up with how much is being published? If you can take photographs with bacteria and program a biofilm to do simple computations like edge detection, what would you do next? Are there practical applications of this? Most people don't read research papers. Who has time for that? But as bionauts, you have this superpower now to connect the dots between what people are saying about bioengineering, the headlines in the newspapers with claims about curing diseases or degrading plastics or some other super innovation. Those newspapers, they're selling you a story. They're giving you the headline, which is what the people, are hoping to get to you. But the research paper is where the reality lives. And so you now have this superpower of being able to connect the headline, the claim, down into the reality, and then to critically evaluate whether or not that claim's real. So see if you can find a news release about a recent bioengineering breakthrough, a disease cure, an environmental solution. And if you can find that, then see if you can link that claim, that news release, back to the primary research paper, and can you parse it? The more you practice that, the more of a biocitizen you can be, and you can enable those around you to be biocitizens as well. Don't believe the hype. How good are you right now at reading a research paper? I bet everybody, could learn how to play chess pretty quickly, but it might take you a while to become a grandmaster at chess. How much better do you think you can get at reading bioengineering research papers?
All right, that was really cool.
We're going to explore.
All right, that's cool. So yeah, basically, this thing, this lecture is telling us uh, to skim those research papers or parse those research papers. That's really cool. Yeah, I didn't know that Stanford professors are also telling you to just skim these as fast as you can. Don't waste your time. There's so many research papers out there. Wow. All right.